Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. Imagine this scenario. You are thinking about studying for tomorrow's exam, but you would rather hang out with your friends. Your friends will make you feel happy, and so to you that's a reward. You get a dopamine hit. If you study tonight, you're going to feel tired and bored, and maybe your dopamine will decrease, so that's sort of like a negative reward. So why do we study for exams? Because we don't just think about immediate rewards. We design a plan of action based on future rewards too. If you study, you'll do well on your exam, you'll get good grades, and you'll get a good job that pays well. So we want to assign some value for being in the state, you staying at home studying for your exam. We call this the value function, and that's what we're going to talk about in this lecture. Now let's think of this in the reverse direction. You receive a reward, let's say that is getting hired for your dream job. Now if you look back at the various things you did in your career and at school, what would you attribute your success to? What state of being in your past led you to get your dream job today? The credit assignment problem is the problem of answering the question, what did you do in the past that led you to the reward you are receiving now? In other words, what action gets the credit? The credit assignment problem shows up in online advertising too, but in a different form. In online advertising, it's called attribution. The idea is, if a user eventually converts and buys your product, but 10 different ad networks showed your ad, who takes the credit for the conversion? There are various schemes for distributing the credit, like assigning the credit linearly. But you can see that for us it's a much deeper problem. Maybe it was the act of showing the user the ad 10 times that made them want to buy your product. So in that sense, all the ads deserve to get the same credit. But perhaps the user didn't see the ad the first 9 times, and perhaps something else on the page was more interesting to look at. Maybe they only saw the ad the 10th time. So in that case, only the 10th ad deserves to get the credit. So in reinforcement learning, we're interested in the entire state sequence and how that particular sequence led to the final reward. Now, closely related to the idea of the credit assignment problem is the idea of delayed rewards. Keep in mind these are all just kind of different ways of saying the same thing, and the solution is also the same. Delayed rewards are just looking at the problem from the other direction. With credit assignment, we're looking into the past and asking, what action caused the reward we're getting now? With delayed rewards, we're asking, how is the action I'm doing now related to the potential rewards I may receive in the future? The idea of delayed rewards tells us that an AI needs to have the ability of foresight or planning. Planning is actually a field of study that crosses over with reinforcement learning. Imagine this scenario. You are in state A, which is the second last state in the game. There are only 2 possible next states, B or C, and both of them are terminal states. B gives you a reward of 1, and C gives you a reward of 0. You have a 50% probability of going to either state. Perhaps your agent doesn't yet know which one is best. We can think of the value of state B as 1, and the value of state C as 0. So what is the value of state A? We can think of it as 0.5, since it's the expected value of your final reward, given that you have a 50% chance of ending up in either terminal state. Now let's say you're in state A, and state A can only lead to state B, and there is no other possible next state. If B gives you a reward of 1, then perhaps A's value should also be 1, since the only possible place to end up is with a final reward of 1 once you reach A. Thus, the value tells us about the future goodness of a state. So we can make this a little more formal. We actually call this value the value function. It's a measure of the future rewards we might get. I think the term value function is a pretty horrible name since the term value is very ambiguous, but it's part of the reinforcement learning nomenclature. It's easy to get rewards and values intermixed. The difference is the value of a state is a measure of the possible future rewards we may receive from being in that state. Rewards are immediate. i.e. jumping on a Goomba will immediately increase your score. Standing in front of a Goomba will not increase your score, hence will not yield any reward. However, being in this state has value because we can soon jump on the Goomba and get the reward in the future. So standing near the Goomba prepared to jump might have a higher value than standing on the other edge of the screen from the Goomba. We therefore choose actions based on the value of the next state, rather than the reward we would get by going to that state. The reward is the main goal, but we can't use the reward to tell us how good a state is, since it doesn't tell us anything about future rewards. One way to think about the value function is that it's a fast and efficient way of determining how good it is to be in a state, without needing to search the rest of the game tree. You could try to enumerate every possible state transition in the game, and determine all state transition probabilities, but you can imagine that would be a time-consuming task. In fact, most games would be computationally infeasible. Tic-tac-toe is easy since it's only a 3x3 board, so the number of states is approximately 3 to the power 9, or 19,683. But that grows exponentially with the size of the board. For example, if you have a 4x4 board like in Connect 4, then you get 3 to the power 16, which is 43 million. So as you probably already know, exponential growth is never good. Searching the state space is only possible in the simplest of cases. Hence, a value function that can tell you how good you'll do in the future, given only your current state, is extremely helpful. Now, I haven't told you how we can actually find the value function, so we don't even know if it's possible yet. But what we're saying is, if we did have it, then that's the information it would tell us, and it would tell us that information instantly, without needing to create an entire model of the game tree and transition probabilities. In fact, this is a constant time lookup, because a state directly maps to a value. You would presumably store the values in an array, which have constant time lookup. This problem, by the way, is yet another instance of the curse of dimensionality, which we've seen in my other machine learning courses as well. Estimating the value function is a central task in reinforcement learning, but note that not all reinforcement learning strategies require it. For instance, a genetic algorithm simply spawns offspring that have random genetic mutations, and the ones who survive the longest will go on to spawn offspring in the next generation. So by pure evolution or natural selection, we can breed AIs that get iteratively better at the game. This is, however, not the type of algorithm we're interested in for reinforcement learning most of the time. Okay, so let's get to the math. The value function, as we talked about, takes in one argument, the state. So we denote it as V of S. It's the expected value of all future rewards given that the current state is S, or in other words, the average value of all possible future rewards given that the current state is S. Pretty simple. We'll define the concept of value more rigorously in a later lecture. Now let's look at a generic algorithm we can use to find the value function. In this section of the course, we're going to introduce some unrealistic constraints so that the problem can actually be solved, but you'll see in the later sections that we won't need to do this. The algorithm we'll use is an iterative one, meaning we'll run a loop, and each time we go through the loop, we'll get closer and closer to the true value function. So the first thing we do is initialize the value function. For all the states where the agent wins, we say the value is 1. For all the states where the agent loses or it's a draw, we say the value is 0. For all other states, we say the value is 0.5. For the algorithms we'll look at in the future, we won't need to do such careful initialization. One way you can interpret the value function for only this game, but not in general, is it's the probability of winning. The value is always going to be between 0 and 1, so this makes sense. The update equation looks simple, but there are some hidden details. So it kind of looks like gradient descent. We take the value function at a state, V of S, and we update it by doing plus the learning rate times V of S prime minus V of S. So V of S prime is the next state, V of S is the current state. The first detail is that S here means all states that we encountered in an episode. So that means for each iteration of the loop, we actually need to play the game and remember all the states we were in. We then loop through each of the states in the state history and update the value using this equation. Notice that the value of the terminal state will never get updated because this equation updates a state's value based on the next state value, which does not exist if we're in a terminal state. Or in other words, if S is terminal, then S prime doesn't exist. So in pseudocode, it might look like this. We loop through the maximum number of iterations, we play a game, we get the state history from the game, and then we loop through the state history and we run through the update equation. The next detail we have to talk about is how to actually play the game. Are we just going to take random actions? In this case, we don't have to, since we have the value function. The value function tells us how good a state is based on how good the future states will be. So all we need to do is perform the action that leads to the best next state. In pseudocode, that might look like this. We loop through all the possible actions that will take us to all the possible next states, and we look at the V of S prime. If V of S prime is greater than the maximum V we've seen so far, we save it and we save that action. Now what's the problem with this strategy? The problem is the value function isn't accurate. If we already had an accurate value function, we wouldn't need to do any of this work in the first place. You might recognize this problem as a problem we already talked about. It's the explore-exploit dilemma. In particular, by taking random actions, we can learn about new states that we would have otherwise never gone to. By doing so, we can improve our estimate of the value function for those states. But in order to win, we need to do the action that yields the maximum value. So we'll be using the epsilon greedy strategy to make a trade-off between exploration and exploitation. Let's look at some intuition for why this iterative update works. First, you'll recognize this update equation from before. It should remind you both of the low-pass filter and the iterative average finding equation we saw earlier. It should also look like gradient descent if you've encountered that in the past. V of S prime is like the target value, and we want to move V of S towards that value. However, with reinforcement learning, there are multiple possible next states, so there are multiple S primes. So by doing this update equation multiple times, we're pulling V of S in multiple different directions all at once. The idea is that by playing infinitely many episodes, the proportion of time we spend in S prime will approach the true next state probabilities. One extremely important detail that's also extremely difficult to discern, given only the update formula, is the order in which you have to update the values for any given state. We know that for any particular episode, we're only going to be updating the values for the states that were in the episode. But the key with this equation is we're moving V of S closer to V of S prime. That means we're doing this update under the assumption that V of S prime is more accurate than V of S. For the terminal state, this is true, since that's always going to be 0 or 1 and will never change. But if both V of S and V of S prime are of the same accuracy, as in they are both not accurate at all, then making one closer to the other won't make anything better. So the idea is we want to move backwards through the state history, because the current state value is always updated using the next state value. Then we want the next state value to be more accurate, so we should update the values in reverse order. This is also consistent with the terminal state being precisely accurate with a value of 0 or 1 that never changes. So let's summarize what we just talked about. First, we looked at the credit assignment problem and the concept of delayed rewards. This is the idea that an action you take now doesn't necessarily lead to a reward right now. In fact, it might lead you to a reward many steps ahead. A great example of this is studying. Studying right now will probably just make you feel tired and miss out on hanging out with your friends. so in fact it might even be a slightly negative reward. But the future reward is that you do well on your test, you get good grades, and you get a high-paying job. We looked at the value function as a solution to this problem because it tells you how valuable being in a state is, which makes considerations for future rewards as well. This entire course is in fact devoted to showing you algorithms for how to determine a value of a state. We looked at the problem from a computational perspective, the fact that a tree of all the possible game states and transitions will grow exponentially means searching it to find a value of a state is infeasible. We therefore use an iterative algorithm, which essentially brings the value of a current state closer to the value of a possible next state. Since there are multiple possible next states, the algorithm is stochastic, but in the long run it should approach the mean or expected value. Throughout this course, we'll see variations on this same idea over and over again. One small warning though. The value function we're learning about in this lecture is not like the formal version we'll learn about later and use throughout the rest of the course. Everything in the tic-tac-toe section is informal, just to get you used to the whole process of solving a reinforcement learning problem. Since this is so abstract, I think the most useful thing we can do now is to start looking at some code to see how we can implement this. Or in other words, look at how we implement this algorithm in a computer and carry out this strategy.